Hello everybody, and welcome back. In today's video, I want to talk about the first two collection types that we have available in Go, arrays and slices. Now, arrays form the basis of slices, so I want to start our discussion with those. And when we talk about arrays, we're going to talk about how to create them, the built-in functions that Go offers us to understand what's going on with our arrays, and then we'll do some exercises working with arrays and see how we can use those in our applications. Then we're going to follow the same pattern, but we're going to switch over to slices. So we'll learn the various ways that we can create slices, we'll learn the built-in functions that we can use to understand what's going on with our slices, and then we'll do some exercises working with those. Okay, so let's go ahead and get started by learning how to create an array. So the first thing that I want to discuss about arrays is the use case for them. Why do we need them, and what are they used for? So let me just drop in an example. Let's just say that we're building an application that's going to work with the grades of students in a class. So without arrays, we're going to end up with an application something like this. We're going to have maybe grade 1, grade 2, grade 3, and then we can print out those grades. So we can go ahead and run this, and we see that we get the scores 97, 85, and 93 printed out. Now this works sort of, but we got a lot of problems here because our application needs to know exactly how many grades we have to work with at the time that we're designing the application, and working with these grades as a collection becomes very cumbersome. So enter the array, and that's going to solve all of our problems. So in order to see what an array looks like, let's go ahead and delete this code here, and then we'll create an array that's going to hold the grades for us. Now the way we declare an array is we're going to start with the size of the array. So we're going to use square brackets, and then we're going to have an index that's going to be the number of elements that our array can hold. And then the type of data that the array is going to be designed to store. So an array can only store one type of data. So in this case, we're declaring an array of integers that can hold up to 3 elements. If we wanted to hold a different type, say we wanted to have an array of strings, then we would type this to a string, and so on. So you have to specify at the time that you're declaring the array what type of data you're going to store. And then we can use this initializer syntax to put in the values for our array. So we can put in the same scores that we had before, 97, 85, and 93. And then if we come into our print statement here and add our grades as what we're going to print, then we see that we have all of the grades printed out together in this collection called an array. Right now, that's a convenient collector. As we start getting into looping constructs and things like that, we're going to really find that having things grouped into arrays and slices and the other collection types is a very powerful way for us to work with our data. Now another advantage that we have with working with arrays is the way that they're laid out in memory. So if you declare 3 different variables and specify their values, it's impossible to know how they're going to be laid out by the Go runtime. With arrays, however, we know by the design of the language that these elements are contiguous in memory, which means accessing the various elements of the array is very, very fast. So by collecting our data together in arrays, not only is it easier to work with, but it also makes our applications generally a little bit faster. Now one problem that we have in this example here is if you look at it, we're actually declaring the size of the array twice. Because we have this syntax here where we're saying that we're creating a 3-element integer array, but then we're adding 3 elements to it. And that's not really required. If you're going to be initializing an array literal like we're doing here, then you can actually replace the size with these 3 dots here. And basically what that says is create an array that's just large enough to hold the data that I'm going to pass to you in the literal syntax. So in this case, we're going to get an array that has 3 elements in it, and that's implied by the fact that in this literal syntax, we've passed 3 integers to it. We can also declare an array that has a certain size, but has its values zeroed out by doing something like this. If we declare an array called students, and let's make that a 3-element array that's going to hold strings, and then let's print out what we have in that array. So if we print out students, make sure I'm spelling everything correctly and run this, then we see that we have an array that's empty. So we have declared a 3-element array that can hold strings, but obviously there's no elements in there right now. So in order to specify a value in the array, we're going to use this syntax. So we're going to call upon the array, and then we're going to tell it which index we want to work with within the array. So in this case, we're working with the 0th index of the student's array, and then let's just assign the name Lisa to it. And then we can go ahead and print out our array again and run it. And now we see that we have, I always forget to add this line return here. Then we see initially we have an array of students that's full of empty strings. In the second instance, we've actually specified that first element. Now you may be wondering why we're starting with the value 0. And the reason is related to how arrays are made up of contiguous blocks of memory. So when we talk about students as the name of the array, what Go is going to do is it's going to have a pointer, or it's going to remember the location of the beginning of that array. And then the index that we pass, in this case 0, is going to tell it how many strings to walk forward. So it knows that when it has a string has a certain length, and so it's going to walk that many strings. So when we pass 0, it's going to be the head of the student's array moved forward 0 string elements. And so that's going to be the first element of our array. So we can finish this example out. If I drop some code in here, we can see what it would take to fill out this array. So in this case, we got the 0th element still Lisa, the first element is Ahmed, and the second element is Arnold. So if we print that out, we see the expected result where we have Lisa, Ahmed, and Arnold. And it doesn't matter what order we work with these. If we flip these around, then we find that they do flip around in the array. We can assign them in any order that we want. Now, if we want to add a specific element in the array, then we can use this square bracket syntax again and dereference the element from the array. So if we do this and then change our label again, so we're going to get the second element of the array, which is index 1. Then we can go ahead and run this, and then we see that the second element has the value Arnold. So we can use this square bracket syntax in order to assign values to the array, as well as to pull out the values that have been assigned. Now, another thing that we can do is we can determine how big the array is. Now, obviously, we created the array up on line 8, so we remember at design time that we created this, but there may be a situation where you need to go back and review the size of the array that you're working with. And the way that we can do that is using the built-in length function. So if I drop in another print statement here and format that, you see that we can get the number of students in an array using this built-in len function and passing in the array. So if we run this, then we see that we get the number of students equals 3, and that's going to print out the size of the array. So if we change the size of the array to, say, 5, then the results of printing out the array isn't going to change, but the size of the array does. Now, one thing that's important to remember is that an array can be made up of any type. It just always has to be the same type for a given array. So we've been working with arrays of integers and arrays of strings, so we've been working with primitives. But this example here shows that we can actually make up arrays of anything else. So in this case, we've got an array of arrays. So let's just say that we're working with some linear algebra, and we need the identity matrix, which is a concept that's used pretty often in linear algebra. So this array here stores a 3 by 3 identity matrix. So the first row is going to hold the values 1, 0, 0. The second row is going to hold 0, 1, 0. And the third row is going to hold 0, 0, 1. So if we go ahead and print this out, then we see that we do in fact get those values. Another way to look at this that may be a little bit easier to see is using this way here. So we're just going to declare the array of arrays, and then we're going to initialize each one of those rows individually. So this reads a little bit cleaner and might be a little bit easier for you to understand what's going on. And if we run this, we get the exact same result. Now, the last thing that I want to talk about with arrays is something that's a little bit different with arrays in Go than in other languages. And that is that arrays are actually considered values. So in a lot of languages, when you create an array, it's actually pointing to the values in that array. So if you pass things around, you're actually passing around the same underlying data. But in Go, that's not true. When you copy an array, as we're doing on line 9 here, you're actually creating a literal copy. So it's not pointing to the same underlying data, it's pointing to a different set of data, which means it's got to reassign that entire length of the array. So if I run this, you'll see what I'm talking about here. So on line 8, I assign an array. On line 9, I create another variable b and assign that to a. And then on line 10, I change the second element of the array to the value 5. And what you see is that when I print out the array a, it has the original values of 1, 2, 3, but b has the new values of 1, 5, 3. So when you're working with this, you have to be a little careful, because copying arrays, especially when we get into functions, if you're passing arrays into a function, Go is going to copy that entire array over. So if you're dealing with a 3-element array, that's not a big deal. If you've got 1,000,000 elements in your array, that could slow your program down a little bit. So what do you do if you don't want to have this behavior? Well, we haven't talked about it yet, but I want to give you a hint right now in order to cover this completely. And that is this idea of pointers. So the way that our program is working right now is that the value b is assigned to a copy of the array a. But if we do the address of operation, which is this character here, then what we're saying is b is going to point to the same data that a has. Now, we'll get into more detail about what this means later, but the long and the short of it is, if I run this, now A and B are pointing to the same data. So A is the array itself, and B is pointing to A. So when we change the value in line 10, we're actually changing the same underlying data for both. So when we print them out, we see that the array A has changed, as well as the array that B is pointing to, because they happen to be exactly the same array. Now, arrays are very powerful, and there's a lot of use cases where you can use arrays very efficiently. However, the fact that they have a fixed size that has to be known at compile time definitely limits their usefulness. So in Go, the most common use case for using arrays is to back something called a slice. So let's take a look at a slice. So the first thing that I want to do is comment out a couple lines in this example here. So we'll comment out this one, and this one, and then we'll change this over to slice syntax. So the way we're going to do that is simply by eliminating these three dots here. So a slice is initialized as a literal by just using the square brackets, the type of data we want to store, and then in the curly braces we can pass in the initialized data. So if we go ahead and run this, we see that we get the values 1, 2, 3. It looks exactly like an array. And as a matter of fact, everything we can do with an array, we can do with a slice as well, with one or two exceptions. So in order to illustrate that, we had the length function that we talked about with an array. Well, we have the length function with a slice as well. So if I run this, we see that we do get the length of 3. So we initialize the slice with the values 1, 2, 3, so with 3 elements. So the length function gives us a value of 3. Now there's an additional function that we have available with slices, and that is the capacity. And that's because the number of elements in the slice doesn't necessarily match the size of the backing array, because the slice is really a projection of that underlying array. So we can have a very large array and only be looking at a small piece of it. Now if we run this example, we see that the capacity function returns a value of 3. So the underlying array is exactly the same size as the slice. But as we go along here, we'll see how we can get into situations where the length and capacity are different, and why that's a very good thing. Now, unlike arrays, where we had this syntax here and we had to use this address of operation in order to point to the same data, slices are naturally what are called reference types. So they refer to the same underlying data. So if we run this example again, remember when we ran this with an array, we saw that B stored different data than A when we were done. So if we run this, we see that A and B are actually pointing to the same underlying array, and so when we change the value in B, we get a change in the value in A. So this is one thing that you're going to have to keep in mind when you're working with slices. If you got multiple slices pointing to the same underlying data, you have to keep in mind, if one of those slices changes the underlying data, it could have an impact somewhere else in your application. Now, so far, we've only looked at the literal syntax for creating a slice, and that's what we're seeing here on line 8. There's actually several other ways that we can create slices, and that is illustrated with this example here. So you see on line 8, we're creating a slice that has the values 1 through 10, and then on line 9, we're creating a slice B, and that's using this bracket with the colon in between. And what that's going to do is that's basically going to create a slice of all the elements of what it's referring to. So it's going to create a slice of all of the elements of A. On line 10, we're creating a slice C, and that's going to start with the third element of the parent and copy all the values after that. So that's going to start with the element with index 3, which is of course the fourth element, and every element after that. So this is going to copy 4 through 10 into the slice at C. Then on line 11, we're going to do the other syntax, and that's going to copy everything up to the 6th element, and that's the literal 6th element. That's not element number 7. That's actually the 6th element, which is going to have the index 5. And then on line 12, we actually see an inner slice. So we're going to copy the 4th element through the 6th element into our new slice. So let's go ahead and run this and see what prints out. So we see the first line printed out is the original slice that we have. The second line is the copy of that slice that's copying all of the elements. The third line is going to copy the 4th element on, so we see the number 4 through 10. The 4th line copies everything up to the 6th element, so we get the values 1 through 6. And then the last line printed out is a slice from 3 to 6, and so we're going to get the elements 4, 5, and 6 printed out. So that can be a little bit confusing because the first number has a slightly different meaning than the second number. So basically, the first number is inclusive and the second number is exclusive. So for example, if we look at line 12 again, we're going to copy from index 3 up to but not including index 6. So that's another way that you can look at it. Now, one thing to keep in mind, remember what I said, that all of these operations point to the same underlying data. So if we take element 5, and change that value in the A slice and run this again, notice all of them change their value because they're all pointing to the same underlying array. So each one of these operations includes the 5th index in their results, and each one of those gets updated to the value of 42. Now another thing to know about these slicing operations is they can work with slices like we're doing here, but they can also work with arrays. So if you remember, if I put these 3 dots in here, it's actually going to turn A into an array. And if I run this, we get the same result. And that's because slicing operations can have as their source an array or a slice. So whatever type of data you're working with, as long as it's one of those two, you can use these slicing operations. Now the last way that we have available to us to create a slice is using what's called the make function. And that's a built-in function that we have to work with. So if I delete all this and drop this guy out, we're going to use the built-in make function, and this takes 2 or 3 arguments. So let's start with 2 arguments. So the first thing we're going to say is the type of object that we want to create. So you can use make for several different operations. In this case, we're going to be talking about making slices. So in this example here, we're going to make a slice of integers. The second argument is going to be the length of the slice. So in this case, I want to start with 3 elements. So now let's just get some information about the slice that we created here. And we'll do that by dropping in a couple of print statements. So we'll print out the values of the slice, the length of the slice, and the capacity of the slice. So if I run this, no big surprise, it's zeroed out. So when I create a slice, everything gets set to the 0 value, which is what we always expect in Go to happen. Every time we initialize a variable, we expect it to be initialized to the 0 values. And that's true for slices just like it's true for primitives. When we ask for the length, we get a length of 3. When we ask for the capacity, that's also set to 3. Now we can also pass a third argument to the make function, and that's going to set the capacity. So keep in mind, the slice has an underlying array, and they don't have to be equivalent. So if we run this, we see that we've created a slice of length 3. It's got 3 elements in it, but the underlying array has 100 elements in it. So why would we do that? Well, the reason is because, unlike arrays, slices don't have to have a fixed size over their entire life. We can actually add elements and remove elements from them. So in order to show you an example of that, let me drop in another example here. And this is going to start with a slice of integers that starts with no elements in it. So if we go ahead and run this, we see what we expect. We see an empty slice, length of 0, capacity of 0. Now if I want to add an element to this slice, I can use the built-in append function. So this takes 2 or more arguments. The first is going to be the source slice that we're going to be working with. So I'm going to start with A, and I'm going to add an element to it. And in this case, all I want to do is add the number 1 to it. And then let's go ahead and print out the value of the slice, the length of the slice, and the capacity of the slice again. So if I go ahead and run this, we see that in the second operation, we have a value 1 stored in there. We have the length of 1, and notice the capacity is 2. So that's kind of interesting. What happened here is when we initialize the slice to the value A, Go assigned a memory location for the slice. And since it didn't have to store anything, it basically created an underlying array of 0 elements for us. As soon as we added an element, obviously it couldn't fit in a 0 element array. So it had to assign an array for us. So what Go does is it copies all of the existing elements, in this case nothing, to a new array that's got a larger size. So when we reassigned, it actually did create a new array. This one has a capacity of 2, and then it put the value 1 into that array. Now, when we're dealing with small slices like this, things are pretty cheap and pretty easy, even if you're resizing the array quite a few times. However, as things get very large, these copy operations become very expensive. And that's why we have that 3-parameter make function. That way, if we know the capacity is going to be somewhere around 100 elements, you can go ahead and start there, and that way as you're appending elements and building up the slice, you're not constantly copying the underlying array around. Now if you remember when I said the append function can take 2 or more arguments, the reason for that is this is what's called a variadic function. So everything after the first argument is going to be interpreted as a value to append to the slice passed in the first argument. So if we have this example here, we're actually going to append the values 2, 3, 4, and 5 to the slice returned by A. So if we run this guy, we see that we get the elements 1 through 5 created there, and the length is 5 like we might expect, but now the capacity is 8. Now it's not fixed in stone how Go resizes the arrays, but generally what I've seen it does is once it fills up the underlying array with a slice, when you add the next element, it's going to create a new array, and it's actually going to double the size from the previous array. So if we start with an empty slice, we see that the array would initially be of size 0, then it'll go to 2, 4, 8, 16, 32, and 64 elements. So that's something else to be aware of. If you're just over one of those powers of 2, you can actually end up with a lot of memory consumed that you're never going to be using. So again, if you have the ability to come up with a decent first estimate, then that's going to be beneficial to you. Now, one common situation that you're going to run into is if you have a slice of elements and another slice of elements and you want to concatenate them together. So you want to have another slice created that has all of the elements of the first slice and all of the elements of the second slice. So you might want to do something like this. If I convert this over to a literal slice, you might want to run a command something like this. Well, this unfortunately is not going to work. If I go ahead and run this, you see that we're going to get Go complaining to us, and that's because the second argument to the append function has to have the type of the slice. So Go can only accept integers here. It can't accept a slice of integers. But we do have a way around this. So I don't know what it's called in Go. In JavaScript, they would call this the spread operator, where if you add 3 dots after the slice, it's actually going to spread that slice out into individual arguments. So if we run this, this is going to work, and it works exactly the same as if this weren't a slice at all. It's basically going to take the slice and decompose it into looking something like this. So these work exactly the same way, but it's a convenient feature to know about if you have slices and you want to concatenate them together. Now, some other common operations that you might do with slices are stack operations. So let's just say that we're treating our slice as a stack and we want to be able to push elements onto the stack and pop elements off of the stack and things like that. Well, the append function is going to allow us to push elements onto the stack, but how do we pop elements off? Well, we have a couple of different ways that we want to do this. If we want to do what's called a shift operation, which means we want to remove the first element from the slice, then we can do this operation here. And what this is going to do is it's going to create a new slice that starts at index 1, which is the value 2 in this example, and takes everything else from that. So if we go ahead and print out the value of b, we'll see that that has the elements 2 through 5. Now, if you want to trim an element off of the end, then you're going to have to use a different syntax here. So we want all of the initial elements, so we're going to start with a colon, and then we'll use that length operation, figure out the length of the slice, but remember, that's going to return a number that's too large. We actually want to remove an element off. So let's go ahead and do length minus 1, and this will have the values 1 through 4 in it. So it's pretty easy to remove an element from the beginning of the slice or the end of the slice, but what happens if you want to remove an element from the middle? Well, here things get a little bit hairy, because what we have to do is we actually have to concatenate 2 slices together. The first slice is going to be all the elements up to where we want to remove the element. So in this case, we can take the first 2 elements by doing a slice of A and passing in colon 2 for the slice that we want to create. Then we have to concatenate to that all of the elements after the index we want to remove. So in this case, we're removing that middle element. So we'll take from 3 on, and then we have to use this spread operation in order to spread things out so that the append function is happy. So let's go ahead and run this, and then get my syntax correct here. And now we see that we've got the elements 1, 2, 4, and 5. So we've successfully removed an element from the slice. Now you have to be a little bit careful here, because keep in mind, we're working with references to the same underlying array, because these are all slicing operations. There's one underlying array, and everything is being done on that underlying array. So just to show you the havoc that we've created here, let me go ahead and print the value of A out here, and then print the value of A out afterwards, and go ahead and run that. And you see we start out with the elements 1, 2, 3, 4, 5, like we might expect. We do our slicing operation, removing the element from the middle. We get 1, 2, 4, 5, which was what we might expect. But then when we print A out, things look a little weird, because we have that slice that B represents, which is 1, 2, 4, 5. Our 3 is completely gone, and 5 is duplicated. So this is something to be very sensitive about. If you're going to be removing elements from the inside of a slice, using a command like we have on line 10, make sure that you don't have any other references to that underlying array. Otherwise, you're going to get some unexpected behavior. So what do you do if you have a situation like this and you really need A to stay the same and you really need B to change? Well, unfortunately, we don't have the tools to work with this right now, because what we're going to need to do is use a loop to create a copy of that slice that doesn't point to the same underlying array, and then you can make the manipulation. So when we get to the looping section, we'll show you how to do loops, and then you'll have all the tools that you need in order to handle that situation. For now, the only thing I could say is beware of this behavior. And if you get into a situation like this, understand that you're going to have to do a little bit of research in order to make sure that your application responds correctly. Okay, so that covers what I want to talk about with arrays and slices. Let's head into a summary and review what we've talked about. Arrays and slices are very common in Go applications, and I think you're going to see them all over the place as you start to work more and more with the language. So I hope that this conversation has really helped you understand what arrays and slices are and some basics about how you can work with them. We started our discussion by talking about arrays, and we learned how they're collections of items with the same type. So you can't create an array that has strings and integers and things like that. All of the types have to be the same, but it does collect them all together. And as we start to get into conversations about looping and things like that, we're going to find how we get some very powerful tools that we can work with when we're basing our data on arrays and slices. They are fixed size, so when you create an array, you have to specify at compile time how big that array is, and it can never change. So you can't make them smaller and you can't make them larger. There are three different ways that we can declare an array. We can do the literal style like you see on this first line, where we're going to specify the number of elements, and then we use a literal that's going to initialize those elements. However, we do have a shorthand notation that uses 3 dots instead of that first size, and that's going to be a little bit more robust in your application design, because if you run into a situation where you need to add another literal, you don't have to remember to update the size of the array. It's going to update automatically. We also have this third syntax where we can declare a zeroed out array. In this case, we're going to declare an array of 3 integers. Each one of those integers is going to start with the value 0. We also talked about how arrays are zero-based. So we're going to be counting from the head of the array. So the first element in the array has the index 0, the second element has the index 1, and so on. So in this example, if we ask for the index 1 of array A, we're going to get the value 3 out. We have the len function that's going to return the size of the array in case you need to know that some other place in your application, and you want to have a way to be able to handle that robustly that's not relying on the fact that you know at design time how big that array is. You can use the len function to interrogate the size of the array. Anytime you're moving the array around, it's going to copy the underlying data. So if you have a 3-element array and you assign that to another variable, all 3 elements are going to be copied to a new location in memory, and you're going to be working with an independent copy. So that can cause some unexpected behaviors, because if you change that copied array and you expect the changes to be reflected back in the initial array, that won't happen. And it can be very expensive because all that memory has to be allocated a second time. Then we moved on to discuss slices and how they're very similar to arrays. As a matter of fact, they're backed by an array. So every slice that you see under the covers, Go has an array that's holding all of that data for you. There are several creation styles. We saw that we can create a slice by slicing an existing array or another slice. We have the literal style that we can use, which is very similar to the array literal, except for we just leave those 3 dots out because the size of the slice is dynamic, and so it can be determined at runtime. We also saw how we can use the make function. So if we pass 2 arguments to the make function, the first is going to be the type of slice that we want to create. So in this example, we're going to create a slice of integers, and the second parameter is going to determine the length and the initial capacity of the slice. If we need a capacity that's different than the initial length, then we can pass a third parameter into the make function, and that's going to allow us to specify a capacity independent of that initial length. The len function returns the length of the slice itself, whereas the capacity function returns the length of the underlying array. So if, for some example, you want to control the resizing of the slice, you can go ahead and do that, and use that capacity function to understand when you're starting to get to your limits. You can also use the append function to add an element to the slice. Now what that's going to do is it's going to take in a parent slice, and it's going to take in 1 or more elements to add to that slice. Now through the course of that append operation, you can add elements that exceed the capacity of the underlying array. If that happens, then you are going to trigger a copy operation, and all of those elements are going to have to be copied to a new location. So be aware of that. If you're dealing with large slices of data and you end up resizing a lot of times, your application performance can suffer. You might want to think about using that 3-parameter make function in order to set the capacity of the slice close to where you need it to be. When you're passing slices around in your application, keep in mind that assigning a new value to an existing slice actually points to the same underlying array. So if you manipulate the slice in one location, it's actually going to affect all the other slices that are pointing to that same underlying data. So we talked about an example where we created a slice and removed the middle element out of it, and we saw how that actually affected the initial slice and could cause some behavior that we weren't expecting. Okay, so that's what I have to talk about with arrays and slices. Again, if I missed anything or if there's anything that's confusing, please feel free to leave a comment down below. I'll endeavor to get your questions answered as quickly as possible. I hope this video was helpful for you. So until next time, this is Mike Vansickle, wishing you luck in your journey to learn the Go language.